For our project, we observed and analyzed the behavior of droplets in two different states: statically, lying still on surface, and upon collision with the surface. We took notice of the size, shape, and movement of the droplets and analyzed them using equations from scientific journals and from our own notes taken during class. We observed the static behavior of droplets through a simple experiment. The experiment consisted of placing one droplet of two substances side by side next to a ruler for scale. The shapes of the two droplets were very similar. The most important observation in this experiment was the difference in radius between the two droplets. The oil droplet had a larger radius than the water one, despite having a weaker surface tension, and we'll analyze this in the next section. The static behavior of the droplet on a surface is primarily categorized by its radius. An equation established by Richard Tolman in 1948 says that a droplet's radius is related to the surface tension of the substance comprising the drop, and a value known as Tolman's delta, which is a function of the intermolecular forces within the substance comprising the drop, where stronger IMF results in a smaller Tolman's delta value. So we found that a droplet of oil had a larger radius than that of water, despite having a lower surface tension. And that's actually due to Tolman's delta being different between the two substances. And the difference is in the IMF, which is intermolecular forces. Water's defining intermolecular force is hydrogen bonding, a very strong IMF, whereas the strongest IMF in oil is actually London dispersion, a comparatively weak IMF. Therefore, oil's delta's value would be larger than that of water. Surface tension and radius in this equation are directly proportional, because as radius increases, so does surface tension. However, radius and Tolman's delta are also directly proportional, so it kind of makes sense for oil with a larger delta value to have a larger radius. For the compressible droplet impact problem, the problem geometry is comprised of a spherical liquid droplet impacting at high speed onto a perfectly rigid body. The most frequently used approximations to the pressure developed in liquid-solid impacts are based on one-dimensional elastic impact theory. According to this model, the generated pressures in the compressed regions are of the order of water hammer pressure. Most of the existing theoretical and numerical calculations are based on the assumption that the droplets are spherical. This is also the case that in the present work, although the shape of impact droplets will always be somewhat influenced by aerodynamic forces acting on its surface. The Weber number, where sigma is the surface tension coefficient, is estimated to be the order of 350,000, pointing out that the surface tension effect in the droplet bulk can be neglected.